aware that Electrochemical Society of India is the oldest society working in the area of electrochemistry, and it is based in IISc Bangalore. So overall plan we had is that in collaboration with IEEE NTC, we plan to conduct a series of lectures so that
I think Dr. Pooja has left. Maybe some networking issue. So maybe we can wait for her. Or Professor Aruna, are you there? Okay. So I think Shweta, you can start by introducing Dr. Saraf to the
Okay.
participants.
Okay. So it is now my pleasure to introduce today's distinguished speaker, Dr. Mohit Saraf, who is a faculty member in Department of Physics and Nanotechnology at SRM Institute of Science and Technology, Chennai. He holds a PhD from IIT Indore and has conducted postdoctoral research at leading institutions including Drexel University, USA, Kiel University, Germany, and the Helmholtz Institute. With over 6 years of research experience, Dr. Saraf specializes in 2D materials like MXene, carbon-based and metal oxide composites, and energy storage devices, including batteries, supercaps, and solar cells. He has received multiple international honors such as Green Talent Award, BRICS Young Scientist Award, and ACS Leadership Award, and serves on the editorial board of several top journals. We are delighted to have him with us today. Without further ado, I request to Dr. Mohit Saraf for his lecture on fundamentals of supercaps, a core area in electrochemical energy storage with growing relevance in next generation batteries, portable electronics, and sensor technologies. We are truly privileged to have him with us today. So before we begin the lecture, I kindly request all the participants to keep their microphone muted. Please feel free to type your question in the chat box. Thank you. So Dr. Mohit, over to you.
yeah, before that, I'm sorry my network went bad. So welcome Dr. Mohit to this series. I was introducing about the Electrochemistry Society. It's the oldest society in India, which is based in Bangalore, and it is a network of people working in area of electrochemistry. So this series is basically to help students understand the fundamental of techniques under electrochemistry. Particularly data analysis is one major problem which we see data recording, so that all their fundamentals are cleared because these are the students who are entering into the research domain. So I believe your lecture planned today on supercapacitor would be highly beneficial. And like as always, told by Shweta, we look forward to interaction of the participant with you. Thank you.
Thank you, Dr. Pooja, for the kind invitation and for introducing the ECS and about this lecture series. And thank you, Shweta, also for my introduction. For the better network point of view, I'll just turn my video off, and I would like to share my screen. Can somebody confirm if you are able to see my screen?
Yeah, it's visible to all.
Okay, and yeah, I forgot to mention, thanks again to the IEEE NTC student chapter, SRM University Electrochemical Society of India, and all other people behind organizing this lecture series. So as the organizer mentioned, that I'll be talking about supercapacitors, particularly about the things I know. I will try to share the usual data recording and data analyzing thing, and a couple of other things. Of course, we can discuss during the discussion session. Before going further, let me introduce a very brief history about supercapacitors. Somebody interrupting? Is somebody asked me?
No, sir. You please carry on.
Okay, so basically in the 17th century, it's all started from developing this Leyden jar. Basically, there is a foil coated on both sides of the glass. Let me just convert this here. So basically, the two metal foils coating were separated by a glass, and they consider as a parallel plate capacitors, which gives a very minute amount of capacity uh, during this jar. So there was need of further developments. And then in 18th century, particularly in 1853, there were some models to describe this capacitive behavior, particularly by the double layer model. So in the 1853, basically Helmholtz describes that it is all because of this double layer, where we have this positively or negatively charged layers from the electrodes, and the opposite charge layer from the electrode side of view, and it makes a double layer Helmholtz model. But it does not take account the diffusion of ions, or basically thermal motion of ions. So in 1910, basically this Goy-Chapman model was proposed, where they basically take account the thermal motion and diffusion of ions, and basically the charge distribution happens. As you go further from the electrode surface, the charge distribution takes place according to the Boltzmann statistics. But again, this model was valid for the low ionic concentration of electrolyte. So it was further improved by the Stern model, where we divide the whole system into three layers: the inner Helmholtz plane, the outer Helmholtz plane, and then the diffuse layer. So this Stern layer is basically the combination of this inner and outer Helmholtz plane. Basically, we have it takes account the thermal motion of ions, and then basically it also follows the Boltzmann statistics. So charge distribution is also there. And till date, there were further several developments in this model. For example, we must have heard about this Conway model and then Marcus model, which discuss about how this double layer behaves when we study this electrolyte interfaces. And Marcus was also awarded the Nobel Prize to further develop this ideal. And then there were further developments, like the first electrochemical capacitor patent was developed by General Electric. And the major development happened in this very high charge storage material, ruthenium oxide, which is very famous electrode material, particularly for its pseudo capacitance. Yeah, basically the development further stated like by several initiative from the government agencies. And then finally in 2000 areas, a lot of electrode materials were developed, and different combinations were also proposed to increase the capacitance or energy by developing different configurations such as asymmetric or symmetric supercapacitors and then hybrid capacitors. And then there was systematic development both in the material design point of view, then how to make this heterostructure electrode where we can improve the properties of materials synergistically while eliminating the shortcomings in a systematic way. And then there was some developments in electrolytes also. Till date, we use different kind of electrolyte system, for example, ionic, aqueous, non-aqueous, and then this very highly concentrated supersaturated electrolyte. And we are in this era where we particularly focus on electrode and electrolyte interfaces with different techniques. Now, before going further, let me tell you that while we mostly focus on electrode materials, there is an electrolyte also which is important, which gives us ions which we store, and then there is a separator between these two electrodes. Basically, it allows ions to move, but it cannot allow electron to move basically between these two electrodes. Otherwise, the cell will short circuited. And then basically we have this current collector for the electron transportation into the system. So supercapacitors, they give very high power and basically very high power density, that because the process happens on the electrode surface, and that is why they can be run over a million cycles, more than million cycles, and that's why their operation life is very long compared to batteries. And of course, since there is a no chemical reaction involved, everything happens on the surface. So it is very fast. But since all the process happens on the surface, there is no bulk process here. so their energy is very limited. And the focus of this area is somehow to improve their energy. As you can see, this formula, that's E is equal to half CV square. If we expand either the voltage or the capacitance, then we can increase the energy of our energy storage devices, particularly supercapacitors, under investigation. Now, a very common analogy to distinguish these batteries and supercapacitor, and particularly this power density and energy density, is that you can use this analogy. Basically, we have this basically a jug which have wider opening. At the same time, you have this can which has very narrow opening. So you can store more amount of water, but you cannot quickly take it out. Whereas in supercapacitors, you can store a lot of water, basically very small quantity of water, but you can take it out very quickly. So basically it has very high power, but energy is limited. Whereas in the case of batteries, you have this very high energy inside it, but you cannot take out very fastly. And similar analogy is given by this another analogy, where you can basically have this marathon race where you are running into 10,000 meter race. So you need constant energy. You need energy for a lot of time. In the case of supercapacitors, like a sprinter, if you are running into 1,000 meter race, so you have to run very quickly, you have to accelerate very fast. So energy is also needed, but your power should be very high. So these are the trade-off between batteries and supercapacitors. And then basically we have different classification in recent times. Also, this was classified based on different charge storage mechanisms. But I particularly like this classification given by the Shah et al. In Chemical Reviews review article, where they say that these materials are particularly divided into two areas: EDLC, double layer capacitor, and pseudo capacitors. And then basically we have this different combination of EDLC and pseudo capacitors. So traditional materials such as activated carbon, graphene, they show this EDLC phenomena, whereas in metal oxide conducting polymers, they exhibit this pseudo-capacitor phenomena. I will explain these terms, what are these. And then we have different combination of these materials, whether we have one, like both sides, we have those capacitive electrode, or one is capacitive and one is non-capacitive electrode. And in similar fashion, we can make this battery kind of hybrid capacitors also, where we have one electrode as a capacitor type, and then another electrode is battery type. And then very recent times, when we have different investigation of materials and electrolytes, then we see that these different materials exhibit different mechanism. For example, these MXenes, which are currently the front runners in this energy storage research. So you will see these MXenes typically exhibit this few capacitance in acidic electrolyte. Whereas if you see the non-aqueous electrolyte, you will typically get this double layer phenomena. So this is another very fundamental when you talk about energy storage devices. So it is typically presented by this Ragone plot. So it's a very old kind of plot where you see this power versus energy values of different kind of devices. You see this supercapacitors is standing somewhere here where they have some limited energy, but their power is still very high. On the other side, these batteries, they have very high energy, but there is power limited. So there is a trade-off, and somehow the focus is to reach up to this point. And the graph is basically same. It's a very recent graph by Kossi et al. So if you see, the research is going on somehow to reach this point where we have this high power as well as high energy. So in electrochemical capacitors, basically this blue graph belongs to electrochemical capacitors. Basically, how we can reach up to this point, because everything happens on the surface. So if we develop this redox material such as MXenes, so we have the provision to reach up to this point. Whereas these batteries, high energy devices, if we try to make high rate batteries, so you lose their life. And that is why basically, you see this dot circle. If we try to basically make high rate batteries, then they lose their cycle life. So and also basically it takes time to charge your batteries because of several limitations such as solid state diffusion and phase transformation. So the focus is to focus for the battery communities to somehow make nanomaterials with better electron transportation. And for the supercapacitor community, somehow to introduce the redox energy storage, and then in a synergistic way, we can somehow reach up to this point where we have this high energy and high power. And this is a very quick comparison. I want particularly to focus in this point. Basically, it was a little old comparison by this leading manufacturing company of supercapacitors and batteries. So the maximum specific energy we get from supercapacitors is 5, whereas from the lithium-ion battery system, it is approximately 100 to 200. And of course, there is a major change nowadays. We can get more than that. But this completely shows that we need materials or electrolyte system to improve their energy densities. And one of the very classical example how supercapacitors and battery work in a synergistic way. It's again a very old example, but beautifully shown here that in a hybrid combination, when the passengers are getting on and off, during at a particular platform, so this shaft comes from the top. Your supercapacitors charges very quickly, and then batteries store that energy, and then you can take another round of 5 kilometers. And similarly, the same kind of installments will be there at different stations. So without using any petrol, any diesel, then with the combination of this batteries and supercapacitors, you can basically travel for a few kilometers, and then again you can charge and discharge it. So the charge storage mechanism, as I mentioned, there's in traditional materials, examples is graphene and activated carbon. It is all basically the electrochemical, electrostatic attraction on the surface, so it is very fast. On the other hand side, if you see this battery type charge storage where the intercalation and deintercalation of ions happen, but it is limited by solid state diffusion and phase transformation, so it is a slow process. But it gives you more energy because we have more charges stored inside it. So pseudocapacitive lies somewhere in between this double layer and battery kind of storage, where the process happens on the surface, but some intercalation happens without any phase changes of the electron materials. So EDLC will be there, as well as there will be some redox. So it gives us more energy compared to double layer capacitors. At the same time, it is fast also. So it is not diffusion control. Basically, there are two phenomena which we all the time discuss in this energy storage system. When it is a surface control reaction, basically we talk about supercapacitors, then it's a non-Faradic process, and it's a surface control thing which is very fast. And when we talk about this Faradic process, which is typical of batteries, we have this diffusion controlled kinetics, we have limitations. And this can be further understood by a fact that this diffusion control thing is typical of this battery type material, which is basically the response is limited by how ions can reach the active sites. And with these formulas, basically current versus scan rate, we can estimate whether the process happening is actually the diffusion controlled or surface controlled. Basically, the process is called as this B value analysis given by Professor Dunn. And basically, you plot this scan rate log versus the peak current log, and you get some sort of graph. So if the value of B comes out to 1, then it is a surface controlled process, and you are basically in the supercapacitor regime. But if the process gives you a value B of 0.5, then basically it is a diffusion limited process, diffusion controlled process. So you are in the battery regime, and in between those, basically you have this mix behavior with both surface as well as diffusion controlled. Again, it's a quick comparison that how these how cyclic voltammograms and galvanostatic charge and discharge profiles vary with different process. I will explain what these CVs and GCVs are in my next few slides. But if you say this is the first indication, when you see any carbon material current response in the cyclic voltammogram, you will see a typical rectangle kind of shape. And of course, the discharge profile will be very basically straight line with no slope, with the constant slope. On the other hand side, for the pseudocapacitor, you will see this quasi-rectangular shape of your CV profile. In the case of batteries, you will see this is dominated by a Faradic process, and in the typical batteries, you will see this very sharp peaks at one particular potential, and you will see these kind of plateaus in your charging discharging curve. So these are typical of these batteries thing. But in the case of pseudocapacitors, you will see that there is an impression of this intercalation, which is basically where there is no evident redox peaks, which can happen because of this intercalation pseudocapacitance. At the same time, you can have this intercalation of ions with the redox reactions. Basically, the partial charge transfer happens, such as in the case of maxines in acidic electrolytes. And then basically there is no plateau, but since this is potential dependence capacitance, so you will see that at every different potential, the capacitance is different. Again, just to summarize that in supercapacitor, generally it is a rectangular shape, and in batteries you have this distinguishing pair of peaks, anodic and cathodic peak. And when you make a full cell, like typically we perform these experiments in 3 electrode configuration and 2 electrode configuration, so you will see these kind of graphs. But when you make this combination of full cell, one is a negative electrode and then one is a positive electrode, so you can enhance the energy. So basically you can occupy the negative regime here and the positive regime here, if you consider that this is a positive. So this is like, double layer capacitive material and then double layer capacitive material. So it's a classical example of this asymmetric supercapacitors, but both electrodes are capacitive. Whereas in this case, you will see that this blue line shows this is a capacitive electrode, but this is a battery kind of electrode, you will see. So when you make a combination of this, it is called as hybrid electrode, basically hybrid capacitor, whereas one electrode is capacitive and another is battery-like. So what is the double layer capacitance? As I mentioned about this model, electrical double layer model, basically we divide this double layer into this inner Helmholtz plane, outer Helmholtz plane, and diffuse layer. So basically what happens is charge storage happens electrostatically. So there is no basically redox reactions happening. Everything happens on the surface, which is very fast, and that is why it will be same throughout. So basically you get this double layer, basically rectangular shape CV curve. And since it is very fast, so you can expect very, very high power density, but it will be limited by capacitance because the charge storage is only on the surface and it is very limited, and that's why you have very low energy density. But since there is no chemical reaction, so you do not lose anything virtually, and that is why their lifetime is very high. So you can basically run this system for over a million number of cycles, which we typically do for the publication, at least 1 lakh cycles for the double layer kind of systems. On the other hand, if you see the pseudo capacitance, you see again the rectangular kind of shape, which is not perfect rectangular, it's a kind of quasi-rectangular shape. So what's happening here is that we have this potential dependent capacitance. So basically what happens is, for example, in ruthenium oxide, which was the first studied material here, so redox happened at each potentials. And when you sum up, it looks like a basically rectangle, but actually it is not so. So it is not purely electrostatic. The charge transfer takes place on the surface. So that is why we call it a Faradic redox reaction happens on the surface. And it is very fast again, because there is no phase change. There is intercalation, but there is no phase change, and there is no solid state diffusion, like the ions are not going to the bulk of material. There is no change in the structure of your electrode. And you might see when you perform your cyclic voltammetry, most likely your anodic and cathodic peaks will be at the same potential. Basically, the peak to peak potential will be very minimal. And as I mentioned, there is no phase transformation and there is no change in the structure of material. So it gives you slightly higher capacitance than the double layer capacitors. And again, as I mentioned about the pseudo-capacitive material, so one is the surface pseudo-capacitance, as you see this quasi-rectangular shape, which is typical in the materials like MnO2 or ruthenium oxide. But we have some other systems, for example, this niobium pentaoxide. And when we study this in LiClO4 in polycarbonate solution, so you will see a signature of redox, but basically intercalation also happens. So you might not see this a complete a rectangular shape, but you will see this envelope basically on the positive potentials again. At the same time, when you change basically electrolyte, for example, this Maxine Ti3C2 in lithium TFSI in PC electrolyte, so you see some sort of some expression of these redox peaks, but it does not follow the ideal rectangular behavior. So we have basically the intercalation is happening. So it's a kind of bulk process, whereas in surface pseudocapacitance, which is very fast, it's a surface process. So when we compare that EDLC and pseudocapacitive, so we have this electroabsorption. There is no redox process, but in pseudocapacitive we have this redox process, and it is very fast. Again, both are very fast, but the amount of charge storage in EDLC is slightly low, but in pseudocapacitive is more. And then again, basically, it can be, you can run this EDLC supercapacitors for million of cycles, whereas the pseudocapacitive such as Maxine can also run for millions of cycles. But still, when you compare with EDLC, it will be low. Again, as I mentioned, that while materials are important, electrolytes also be very important. So if you see that all the electrolytes, such as aqueous electrolyte, water-based electrolytes, they have thermodynamic limit 1.23 volt, and after that 1.23 volt basically the hydrogen evolution and oxidation starts. So we cannot expand our electrochemical window beyond this voltage. But if you take these organic electrolytes or ionic liquid electrolytes, so water is not there, so you expand your window. So let's say if you go from organic electrolyte, you can expand window from up to 4 volt and even beyond that with ionic liquid electrolyte. But they have some associated problems with that. For example, these organic electrolytes, you have to handle them with very care, and they are not environment friendly, and basically they are flammable also. At the same time, ionic liquids, they are very expensive, viscous, and they basically reduce your ionic conductivity of electrolyte. So with respect to sustainability point of view, somehow the research is to improve the property of aqueous electrolyte, and people are exploring by increasing the concentration of solutes ion. So they are transitioning from the salt in water to water in salt electrolytes also. So somehow to make the concentrated electrolytes to expand the potential window to achieve higher energy density. And so we have electrode material, our electrolyte, and typically for supercapacitors, we see many kind of system in our lab. This beaker cell is very famous to do this 3 electrode testing, but we have to take a large quantity of electrolyte here with solvent. On the other hand, we have this coin cell assembly, which gives you great results, but you need the pressure in the lab for that. And let's say if there is a problem, so you cannot disassemble it. So basically, it's a very great system to study these batteries, different kind of batteries. But when it comes to supercapacitors, when you have to open and close these cells again, then there might be some challenge. So on those cases, phase lock cell basically can help you where the amount of electrolyte taken is very low. So we can quickly, let's say if there is any problem, so we can quickly disassemble the cell and basically rearrange everything so that our system works properly. So these kind of Verilog cells are highly recommended for supercapacitor testing. And when you do this electrochemical measurements, let's say your material is ready, your electrolyte is ready, and everything is ready from preparation point of view. So it is always recommended to rest your cells before electrochemical experiment. So basically what that resting does is wetting your electrode is very important. So we have this electrode and electrolyte in an assembly. So your electrode should be properly mixed. Basically the electrolyte should access all the states of your material. So that is why this resting is very important. Typically 30 to 60 minutes for many double layer capacitive kind of materials should be enough. And then we always need to check this open circuit potential. If this OCP is changing, then the first impression is that there is a problem in your system. maybe it is not stable, or the connection in the particular channel is not stable. So basically, if you check the OCP as soon as you assemble your cell on the electrochemical workstation, so it gives you kind of initial basically impression whether your cell is stable or not. And then of course, so basically for supercapacitors, it is always recommended to do preconditioning your cells, or basically pre-cycling your cells. Again, the purpose is just to check whether everything is okay with your cell, and those pre-cycling basically again it wets your electrode. So basically whatever you wants to do, your electrochemical reactions will be stabilized, and then electrolyte will be able to access your materials properly, and you can get the better results. There are some few parameters when you do this supercapacitor testing. So we check this energy, power, what is the maximum potential window you can get, and then capacitance, and of course then this equivalent series resistance, basically which governs basically how this electrolyte resistance is there, how many is there any other interfacial resistance or not, if there are collector, like basically the resistance between the inside component of your cell. So basically this is very there are also some other kind of resistance, for example solution resistance, charge transfer resistance, which we usually study by electrochemical impedance spectroscopy. So very first technique, and personally I like this technique very much in cyclic voltammetry. Basically it is used to study the electrode and electrolyte behavior, basically how the interface works. In this technique, basically we ramp the potential of our working electrode with time linearly to a set of cut potential. So basically we set the potentials and we linearly swap the working electrode. And then again, when it reaches that point, and so we reverse the swap, and then again it brings to the original position. So basically we ramp the potential linearly, and since we basically the potential is ramping linearly, so we have to measure the rate at which we are sweeping that potential, and that is called a sweep rate. So basically it is kind of dividing by of this potential versus the time. So that is called the sweep rate. People call it a scan rate also. Then basically the potential, this is very important thing, that what we are doing here is we are providing the potential between the working electrode and the reference electrode. So voltage is provided between the reference electrode and working electrode, and we measure the current between the working electrode and counter electrode. And then in supercapacitor regime, when we talk about supercapacitor regime, so we usually study them at different scan rates for the kinetic point of view. So typically we use this 2 millivolt per second, 5 millivolt per second, and then we usually go up to 1000 or 2000 millivolt per second scan rate. So once you get your cyclic voltammograph, so you get these kind of curves where on the y-axis you have this current, and then on the x-axis you have this potential. It is important that you always mention which reference electrode you are using. For example, in this we were using this silver wire, so it is important to mention which kind of reference electrode is there. And of course, when you get the current, so you have to divide it by mass to get this current density. This division is very important when you compare different systems. You can also present this current only, but when you compare this different system, then you have to present this as a current density. And of course, at different scan rates, from example, in this example, you are going from inside to outside. So you are ramping your system at 5 millivolt per second to 1000 millivolt per second. So it's a scan rate. And always put how much mass loading is there on your cell. So it's very important to mention the mass loading on your system. So it gives you clear implication whether it's a high mass loading or low mass loading. As we see many times the reviewers ask for all these questions, which sometimes lead to rejection of also. So everything should be available on the figure itself. At least these parameters should be absolutely clear. And when we calculate this capacitance out of this paper, for example, Since this is a kind of battery kind of material, so we typically call this capacity or charge values. So we plot this specific charge value, basically either it is a capacitance or capacity. So do not get confused right now. So just assume that this is a capacitance, and we plot it against the scan rate, and we get these kind of curve. So when we increase the scan rate, you will get less capacitance. Why? Because at higher scan rates, your electrolyte molecules are not able to access the inner spaces of your electrode. So this is like very general. The trend always goes like this. But it is very important to see that whenever you present your data, so you always see that specific capacitance value goes down with increasing scan rate. But actually, it is not so. So for the first impression, let me, if I'm a reviewer, I will always see that what is the behavior of this capacitance against scan rate, and this gives me an impression that, oh, it is decaying very quickly, but actually it is not so. So when you convert the x-axis on the log scale, so you will actually see that the capacitance decaying is not very fast. So basically you see that at 100 millivolt per second also you get a decent capacitance. At the same time, the same data is there, but it looks like that it's a very fast decay. So it is also very important to put the correct log scale on your y-axis to see basically to present your data in a better way. Another thing is when we talk about this double layer capacitive material or pseudo capacitive material, you will see that sometimes people present as a specific capacitance on the y-axis in place of current density. So in place of A by G, you will see this F by G. So that is also C. So when that is also fine. But you cannot do this for battery kind of battery behaving material, because there the current is not directly proportional to the capacitance and scan rate. So this is allowed only for the double layer kind of material, capacitive materials. It is also very important before beginning any experiment that you have to determine the electrochemically stable potential window. So if you have a completely new material, then you have to do a lot of optimization. But let's say if your material is reported and you are studying in a different electrolyte, so first it is always advisable to check the literature and to have a sense about your voltage window. So in aqueous electrolytes, it should not go beyond 1.23 volts. So this is also one impression. But we can expand this window by using concentrated electrolytes. But one of the recommendation is always check the OCP, which I mentioned earlier. And if you want to get a sense of your electrochemical window, so you can slightly change, slightly increase the potential window in both sides until you see this sharp tail on both sides. So let's say at this point it is still okay, but after this point you will start seeing these kind of sharp peak. It may be redox peak, so maybe I won't mind killing my cells first cell actually. So if you see some kind of redox peak, then it is okay. But in the second cell, let's say if it is not happening and you see just the sharp tail increasing, that means the hydrogen evolution has started. So you have to stop from here. So maximum I can go here. So basically, similarly, you do this experiment on the positive side, and until you see this sharp tail because of oxygen evolution reaction. So if you go by this example, your electrochemical stable potential window should be from here to here. So you have to avoid this. If you take account this kind of window, like this window also, so it's okay that in the beginning you will see that your window is slightly large and you get high capacitance and energy. But when you perform the cycling test, basically the cycle life, then it will be very poor, because you are inducing the unnecessary side reactions which will kill your cell faster than in the normal mode. So it is very important to determine your stable electrochemical stable potential window. And similarly, in example, it is clearly shown that if you go beyond this point, the sharp tail increases. So you should cut your potential at this point. Next, this is one of the another example that why this electrochemical stable potential window is important. So this is my cell. First, I basically ran it from 0 to 0.3 volt, and it looks absolutely fine. You see the if you one of very quick trick is just divide your cyclic voltammetry curve and see the upper and lower section. If they look symmetric, if they look equal, I'm saying this, if they look equal, you cannot estimate without integrating the area. But if they look equal, then you are good to go. And then you can calculate the Coulombic efficiency. So Coulombic efficiency is just to see the discharge upon charge. Basically, you can see by the area also. If that is more or less 99%, then it is okay. So you can go further. So in 0.4 volt also, you get very high Coulombic efficiency, let's say 99% or 100%, it's okay. 0.5 volt, it's okay. 0.6 volt, it's okay. But let's say in 0.7 volt, you start losing your Coulombic efficiency. So let's say discharging area is more than charging area, and you get Coulombic efficiency somewhere around 110, like 110%. So that means there is some problem. There is some kind of side reaction. So I will stop there. Maybe I can go up to 0.65 volt also. But for this particular case, I found out that 0.6 volt was giving me a very good Coulombic efficiency. So that should be my electrochemically stable operational voltage. And then while calculating capacitance, we have to take into account the nature of your process happening. For example, here, if it is double layer capacitive material, double layer kind of rectangular behavior, so you can see that we can simply use this formula. It's a typical of double layer materials where there are no sharp peaks. So basically you are just integrating the area under the curve, and then you are dividing it by the scan rates. Delta is basically the potential cutoff from 0 to 0.95, whatever it is. But when it is not your rectangular curve, let's say if you have some redox happening on the C. So first of all, you see one way is to calculate the whole integrated area under the curve, or you can simply divide these into two different sections. One belongs to the oxidation and one belongs to the reduction. So you calculate the capacitance for upper half and lower half. You might see some formula like they divide by 2. That is just because you have two different sections. So you can use this formula. Basically, we calculate this area under the curve, and then we divide it by scan rate and your potential window. So it should be noted that when you do this, the Coulombic efficiency should be good enough. Then only this formula applies. Otherwise, there will be difference between the capacitance you got here and what is obtained here. Another very, very important technique is galvanostatic charge discharge. Sometimes it is very famous with this short name. It's a GCD. In some system, you will see this GPCL also. But let's discuss about this GCD technique here, where we apply the constant current. So whenever you hear the word galvanostatic, galvano word is it belongs to current. So current is constant, and then you change your potential in the both negative and basically positive region. So there are cutoffs. So you basically change the voltage. The current is constant. So voltage changes, then there is a cutoff, and then it comes back, and then there is a cutoff. So basically it goes like this. And basically it is also it also tells about how much charge is stored in our cell or electrode. And in supercapacitors, basically we are interested in very higher current densities, and we can basically calculate which current density to choose based on our cyclic voltammetry data. And this is one of the example. Let's say if your scan rate is 2 millivolt per second, and basically the half of the cycle takes only 5 minutes, then the lowest current density which you choose here will be in the same time scale where your efficiency is 100%. So basically you can calculate how much time is changing, and we can basically insert the value of current density accordingly. And typically we use this kind of current density as 1, 3, 5, and 10. So when we observe the data, let's say if it is a double layer behavior, you will see this symmetric charge and discharge curve with no slopes. Basically, it's a kind of straight line. So you can simply calculate the capacitance by using this formula of current divided by slope, because the slope will be constant at each and every point in this discharge curve. But if it is not the case, if your charge and discharging curve is not linear, so in the non-ideal cases, this will give you an impression that the area under the curve in the charging region and discharging region is different. So the first thing that should come in my mind is their Coulombic efficiency will be different, because if you divide discharge by charging area, it will be different, and the slope at different location will be different. So one, second, third, let's say if they are different points, if you want to take, then basically the slope will be different. So this equation does not apply. So people either use a standard integral equations, or you can estimate, not accurately, but you can estimate your capacitance with this formula, where you simply multiply this current and time on that particular point, and then divide with the voltage window. For more details like how the calculation works here, I recommend you to go through some standard books like Conway and Bird, and then some journals recommended. I will also share a couple of journals at my last slide, like which papers will clear this picture. And why it happens, either you are overcharging your cell, or basically you are insufficient charging is there, which leads to Coulombic efficiency. And when you see this, basically some parasitic reaction starts happening, or some gas evolution is there, hydrogen evolution and oxygen evolution particularly. And it also tells you that there is a strong internal series resistance is there, or maybe it is due to the poor conductivity of the electrode. So there might be several reasons. One very common observation is that this internal potential drop happens during this charging and discharging curve. This is basically due to the electrical contact between your system, and then either it may be due to some electrode resistance or some electrolyte resistance. And basically this equivalent series resistance is a common parameter to calculate how much heat is dissipating from your system. So if basically power loss, so basically you can calculate the power loss based on this ESR using this formula. So it's a parameter that, you know, how internal resistance affect your system, and how you can improve it by improving the electronic conductivity, or making good electrical contacts between the electrodes and the cell. Again, when you get this charging and discharging curve at different current density, so the first thing that should come in your mind is whether they are symmetrical or not. If you draw a straight line, and if you see the area in this side and on this side is equal, then you can basically estimate that your system is coulombically efficient, and you can go for basically calculation of your capacitance. But if they are not equal, then you should redo your experiments, or you should check what kind of basically what is happening with your cell, what is happening with your system, whether your channel is stable. If there is a problem in channel, then you can redo, you can reassemble your cell to improve basically the charging and discharging curve. Or maybe you can limit your potential window. Maybe it was not properly optimized, your electrochemical window was basically overestimated. So you have to check all these parameters. So after doing this cyclic voltammetry and charge discharge experiments, we do this cyclability test basically to test the cycle life of your system. So typically, for the publication point of view, we usually do this 10,000 cycles. But for supercapacitors like carbon material based supercapacitor, we can run over 1 million of cycle. But it should be noted that while you report this capacitance with number of cycles, it is also important to basically mention about this Coulombic efficiency. So this Coulombic efficiency is this blue curve, and it is nearly 100% throughout the 10,000 cycles. So it is very important. This axis belongs to this capacitance, and this axis belongs to this Coulombic efficiency. So it is important to mention about Coulombic efficiency. And you can use either CV or any charge discharge technique to test the cyclability test. And then you can choose a scan rate and current density wisely, where you see all the features of your electrode and electrolyte interface. It is not like that you can choose any random current density, for example 20 ampere per gram, where if the redox happening was at low scan rates, so you simply choose very fast current density or very fast current scan rate, because you don't have anything to lose there. So in that case you will get very high performance, you will get nearly 100% retention, but that is not advisable. You should always choose wisely this current scan rate and your current density. Again, this is not a very basically strong recommendation, but at least from the publication point of view, you have to do this 10,000 cycling, and you have to show the changes before and after cycling. And of course, this Coulombic efficiency is very important. I think I'm already late, so I'll just quickly pass this EIS technique. Also, I'm not very well expert in this particular technique, but you see, in the EIS technique, we usually get two kind of curve, whether it is a Nyquist plot or it's a Bode plot. But these Nyquist plots are very famous, where you basically uh, measure the electrode behavior against the negative or of your impedance, and then there is an imaginary impedance, and then it's a real impedance, and you plot that at different and study them at different frequencies. So basically this region is high frequency region, and then when you go away it is a low frequency region. So you can distinguish the behavior, whether it is double layer behavior. If it is close to the y-axis, then it is a double layer behavior. And if you see that this semicircle and then followed by this line, then it is considered as a pseudo-capacitive behavior. In the battery materials, battery kind of behavior, you will see this semicircle is very large, followed by a 45-degree line. So we can easily distinguish materials based on this Nyquist laws. And of course, it tells you a lot about this charge transfer resistance, then what kind of solution resistance is there, what kind of Warburg resistance is there. So we have, when we get the data out of it, so we basically we study them by equivalent circuit. So we basically check whether which kind of resistance the system might be having, which kind of capacitor component is there, and we make basically different equivalent circuit, and then we analyze them, and based on that we say which component is causing which resistance. Only recommendation from my side to the Nyquist plot is that you should always present as a square. The x and y axis should be equal, which is a major mistake in all the publications. So basically that is done to show this kind of semicircle. Let's say if somebody is showing 100 on the y-axis but on the 15 on the x-axis, and that is just to show your electrode semicircle very clearly. But the recommendation is always to use and show it as a square. And finally, I think I'm reaching the time limit, and the very last slide probably. So here are some of the recommended books and the papers which you can follow, which clearly tells you how to perform these electrochemical techniques. What are the major and most common mistakes people do while analyzing this cyclic voltammetry and charge discharge curve. At the same time, I will also advise you to follow this EChem channel, which is run by my former colleague at Drexel University, John Mang, which gives you how to make your electrodes, how to make 3 electrode and 2 electrode assembly, how to analyze that data, and all fundamentals of electrochemistry. And finally, being an editor, it is my responsibility to do some advertisement. So if you are ready with your any of the work to be published on material side or electrochemistry side, so I asked you to consider these journals for your next paper. And finally, with a special thanks to all these people which helped me making this presentation, I would like to thank each and every one of you for your attention. Thank you.
Uh, Thank you very much, Dr. Sharaf, for the informative and engaging lecture. Your presentation was truly engaging from the very beginning. Starting with the history of supercaps was brilliant way to set the context, and your clear comparison between batteries and supercaps made the difference so easy to grasp. The real life application through the Sunwind bus example added so much relevance and clarity. It really brought the concept to life. Thank you very much. So, such an insightful and well structured session. I'm sure the student and participants have greatly benefited from your talk. So now the floor is open for the question and answer. We can check the chat box. Yes, there is some questions. Yeah, I'm starting from the first question. Okay, so the Vinayaka, so he is asking, or maybe you can see, should I?
Yeah, so I can see. So Vinayaka, thank you for the presentation. I'm starting to work on supercapacitor. I don't know anything about the concept of physics. Where should be starting? So I think my very last slide could be your first slide for starting your knowledge, getting some knowledge out of this. So I recommend reading those journals. Maybe I can share again if you have not taken the screenshot. So I guess you should start reading about the fundamentals, and these are very recent papers and clearly show with good pictures how the system behaves, how to read those graphs clearly. So I think that should be a good starting point for you. And then, of course, all of us are here to help out whatever we know. If we know, then definitely we can help out, or we can take help from some electrochemist if you are troubling with some other electrochemical thing. Okay, so thank you very much. Please explain again how to choose current density. Okay, so basically, when we talk about supercapacitors, so we are interested in higher current densities, and well, there is no high and low when we talk about current density. But let's say if your scan rate in your cyclic voltammogram is 2 millivolt per second. So if you go below that, you are basically transitioning into the battery regime where we charge and discharge our cells very slowly. So if your scan rate is 2 millivolt per second, so you check the timing, how the upper half takes from one cutoff to another cutoff, and based on that you can choose your current density. So when you will write down these things, all the parameters, you will easily get how to calculate this current density because you have your mass. So it's not a big deal. Just focus on the scan rate, how long it takes to reach from one cutoff to another cutoff, and then in that way you can get it. Then how nitrogen and oxygen doped activated carbon have pseudo-capacitance behavior? Kindly explain that. Change. Just a second. It is changing. So if I'm getting this point correctly, so you ask me that if we change the activated carbon surface and dope it with nitrogen or oxygen, so what essentially happens, it depends on your electrolytes. Let's say if your electrolyte ion is going on the surface of your electrode, and basically the charge transfer takes place, then basically you are essentially running the redox reaction on the surface. So you might observe some pseudo-capacitance behavior. So this is what I can think of if I am understanding your questions in a proper way. I want to ask that if we have pseudo-capacitance behavior, then in our GC plot, we could calculate capacitance using discharge time or discharge area. Okay, so see, discharge area will be there if you take account any equation like the integral equation. If you take into account, then again, basically, let's say it's IdV. So you calculate this integrated area under the curve. So discharge time will be there to calculate your discharge area. So basically, try to think, in a complete manner that whether it is a discharge time or discharge area in the equation, basically the area under the curve will come into picture. For the KOH electrolyte, just a second. which is going up as soon as I change it. So for the KOH electrolyte, maximum range is only 0.6 and minus 0.4. What is the reason for this? Yeah, so basically, as I mentioned, that electrolyte changes the electrochemistry. So it is about the mobility of your ions. Let's say if you have sulfuric acid, so the mobility of sulfuric acid proton H ion is very high. So you might trigger the oxidation and reduction very quickly. On the other hand side, let's say if you have OH ions or any other ions, so maybe it depends on how quickly your ions can move in the electrolyte. If it is fast, then maybe you are triggering your oxidation and other events very quickly. And if it is very quickly, then you are limiting the voltage somehow. So it depends on the mobility also of your ions. Nice presentation, thank you. Nice. What are the current advancement in the water in salt electrolytes in the point of view of non-SEI and SEI forming electrolytes? It's a very good question. So basically, this field is expanding. Basically, water in salt electrolyte is nothing. It's a concentrated electrolyte. It's a very saturated kind of electrolyte, and the idea is to expand a electrochemically stable potential window. When you do this water in salt electrolyte, so the amount of water is very low. So the amount of solutes ion is very low. Let's say if it is lithium chloride, so lithium ion will be there in larger quantities than water molecules. So your water molecules are not freely available. They are basically coordinated with the lithium ions and chloride ions. So somehow basically, it gets deposited on the electrode surface, and that is why your water molecules are not available to corrode your surface, which is basically called as SEI layer. So in that way, since water is not able to interact with the electrode surface, so you get expanded window. Now, whether it is in the point of view of non-SEI and SEI forming electrolytes, so in most of the cases, whether it is water in salt electrolytes or any other kind of electrolytes, if SEI formation is there, then in most likely you will get expanded potential window. So if you design your electrolyte in such a way that you do not lose your ionic conductivity, because there is a lot of solute ions, at the same time you can expand the potential window, I think that would be a perfect case in both SEI and SEI for non-SEI forming electrolytes. Sir, in EIS, semicircle is mandatory because most of the time we don't get it. So in basically this semicircle, I'm not well expert, but I can say that this semicircle is basically typical of batteries. It represents the charge transfer resistance. In EDLC material, typically this carbon-based material, you will not see the semicircle, and that is very obvious. But in some cases, like Maxine also show semicircle. But I suggest you to perform those experiments at different potential also. So you will see that your semicircle is not changing, only the straight line that is changing. Either it is coming closer to the y-axis or it is going away to the y-axis. So, in Maxine, it is called as interfacial resistance. So you see, different materials behave differently, and this semicircle, basically in carbon-based electrode, you will not find this kind of semicircle in most of the cases. But if you're finding it, then either what I can think of is either your carbon electrode is functionalized with some other material or some other groups which is triggering some kind of redox reaction at the surface, and then you are able to see those kind of semicircles. But I cannot think any other electrochemical event at this point. Maybe you can give me more details. Nice presentation. I know how you are going to equations finding space for both CV and GCD for an asymmetric for which one? No. So there are two equations I showed you. The equation holds true only. There are two equations. One is for the ideal charge discharge, like linear, and one is for non-linear. For the non-linear, either you can estimate the capacitance with the formula I showed, or you can calculate through the integral equation. If you are still confused, I just refer you to check those papers which I basically mentioned in my last paper. So different people use different equations, and I won't say any of those equation is wrong. Basically, it is a kind of estimation. You cannot control the slope at any point. So you have to use basically either the integral equation, or you can estimate simply by dividing the slope. Yeah, but it will not give you perfect results. What is the maximum voltage window of neutral electrolyte? It depends. It depends. I mean, there is no straightforward answer to this question. But in neutral electrolytes, I feel you can have basically, it depends like which electrode and which electrolyte you are using. What is the concentration? What is, it depends. There is no straightforward answer for this. What is the maximum voltage window of neutral? No. I mean, you cannot say. It depends on a variety of factors. Thank you for a presentation. For all the results in testing, for which it should be 3 electron, 2 electron, and what are the bare minimum testing needed to get work complete specifically for publication? So yes, as I mentioned that 3 electrode testing is very important because it gives you the electrochemical signature of your system. You have very well defined stable potential because you are using a reference electrode. So whatever you measure against the reference electrode. Let's say if you are measuring it against AgAgCl. But when you go for the 2 electrode system, so there is no reference electrode. It is basically done for the full cell or for the device level cell. So when we present any paper, so basically we show that how our system is behaving, and that is done in a 3 electrode configuration. But when you show that how much expansion we can do with the electrolyte, with the voltage window, and how much energy and power is needed, you have to use 2 electrode configuration. So this is another common mistakes. Basically, I think everybody does is that you cannot calculate your energy and power density from 3 electrode configuration. And another thing is very interesting that when I say about this energy and power density, you will see all the Ragone plot which I presented earlier. It is like kilowatt per kg, but actually when you say that it is mass, when you are saying either it is a gram or kilogram, it is not power density, it is a power, specific power actually. So please see that in supercapacitor community now it has become very common that people use power density all the time. Actually, we are not calculating the volumetric power. We are calculating this kind of mass-based power. So it should be specific power. So I suggest always to write specific power or specific energy in place of power density or energy density. Then I think I answered your question regarding the 3 electrode and 2 electrode configuration. Thank you very much for the nice presentation. My question is, where are we currently in supercapacitor? What is the benchmark we are at currently? Like if I talk about water splitting, we have platinum, which is showing highest activity so far, but the weather rather than said, which non-noble materials currently is a benchmark, as I've seen people are reporting too much capacitance. So very interesting questions. See, when we talk about this energy and power performance, whenever you see any capacitance more than 700 or 800, trust me, that is not true. Okay, because when you see any battery kind of behavior in your system, so it should be reported as milliampere hour per gram or charge per gram. It should not be reported as farad per gram. So if you follow papers from the best electrochemist, you will never see those kind of values like 3000 farad per gram. Even if you get more than 1000, let's say 1000 is also very much in the 3 electrode configuration I'm talking about. If you get more than 1000, then either you are miscalculating or there is some problem in your system. Either you have not taken mass correctly or something. The benchmark is nothing. Ultimately, the community is expanding to break the trade-off between the power and energy. if you increase the energy, you lose power. If you increase the power, you lose energy. So somehow the research is aiming towards reaching at the point where we have high energy and high power, but that is never achievable so far. So people are making different combination of materials so that we can get redox energy storage, because that is very fast. As I mentioned, I explained actually in my presentation. So if you talk about any specific materials, there is no benchmark. Still, all the time in the commercial device, we use activated carbon kind of stuff, because many of these fancy materials, when you assemble the device, then you lose your capacitance greatly, like in multifold manner. So you, even when you go from 3 electrode to 2 electrode, basically, and then 2 electrode to device level, let's say if your capacitance, maximum capacitance in 3 electrode configuration was 300 farad per gram. So by the time you reach at the device level, it will be like 5 farad per gram or 3 farad per gram. So that's why I'm mentioning that there is no benchmark. Somehow we have to break this trade-off between energy and power. And you can report 10,000 farad per gram, but if it is not giving any real world value, then there is no meaning actually. Maximum time when I'm working with nickel form electrode, it is difficult to attain long cycling stability. I'm using 1:1 centimeter area for drop casting material, and complete dimension is 2:1 centimeters for clipping. What point should I consider for better results? Honestly, I'm not a big fan of nickel form, because I tried it once and I saw many papers, let's say Maxine with nickel form they were using, and it shows you redox signature. Okay, what is happening is it's a nickel redox rather than your Maxine redox. Similarly, if you drop cast or if you coat your material with nickel on nickel form, so if your coating is not optimized, so maybe you are forcing nickel to give redox activity rather than your material, or maybe it is a combination of your material and nickel form. So basically, with my limited experience with nickel form, I cannot say much, but I feel your system, your material is not properly attached to your nickel form, and that is why your electrolyte either reaches to the nickel form, or it is not properly reaching to your inner spaces of your electrolyte. So basically, the electrode and electrolyte interaction is poor. And there might be some other reason, if the structure is basically destabilizing during the electrochemical activity, then also basically it can hamper your result. So at this point, since it is a drop casting, again in drop casting, I don't think it will be a very good attachment of your electrode with the electrolyte thing, your material with the substrate, with the nickel form. So there might be many possibilities. Without proper checking, it is difficult to interpret at this point without checking the pictures, digital pictures of your system. So what I suggest you to do, SEM image before and after, like let's say if you do 1000 cycling, even if your performance is degrading very quickly, it is absolutely fine. So you just do some post-mortem analysis, and if you see significant structure distortion in your sample, then I think that might be one of the possibilities. Very informative session. Thank you. Synthesized transition metalite nanocomposite. I need CV characterization facilities. I mean, I would suggest to ask your supervisor or the colleagues in which institution you work. I think that would be a better choice rather than asking me. I am also new. Very recently I joined. I'm in the process of establishing my lab. But many people are here. Dr. Pooja is also here, so maybe you can approach them also. But I think it should not be a problem as long as you are working in some institute. Is there any application of hybrid capacitors? Well, the application of capacitor is always to store the energy. So I mean, there are so many applications of capacitors, whether it is hybrid, whether it is symmetric, or it's a simple supercapacitor. So yeah, I mean, so many applications. is there any application of hydrogen? Is there any way to increase the discharge time of supercapacitors? Why you want to increase the discharge time? There is no point of increasing the discharge time. If you want to increase, it should be charging and discharging should be high than your other system. And the only, I mean, if you ask me experimentally, I would simply say that use lower current densities. Your charging and discharging will be high. But I think you don't want to ask. I think you want to ask how to increase the capacity. And I think I have provided enough method how you can increase the capacitance by tailoring the morphology. Somehow you can reduce the short. You can somehow access the electrode surface efficiently by somehow creating those short diffusion channels. And of course, you can get some electrical conducting material or additive with your system. Then I think you can improve your performance. And of course, large surface area of your electrode structure so that you can capture more electrolyte ions. In CV, I got redox reaction in the range of 0 to 0.8 volt, but while performing GCD, the potential of 0.8 volt is not attained. What might be the reason, sir? The potential of 0.8 volt. See, if you have optimized your electrochemical window in CV to be 0 to 0.8 volt, then in GCD you will surely get 0 to 0.8 volt. It is possible that your optimization in the CV itself was not correct. But if it is not coming in GCD, I think there is some problem. So ideally, you should always present the same electrochemical window in CV as well as in charge discharge. So there is no point explaining this point. I think you should just redo optimization, just re-optimize your system. Your potential window should be equal in both CV and GCD. And if you are seeing the redox in CV, then you will definitely see in the GCD also, provided you choose the appropriate current densities. If you are choosing your current density to be very fast, but you recorded your CV at low current density, low scan rate, then there might be another problem. So choose your current density wisely. As I mentioned, that you can just check the time, how long it takes from reaching one point to another point, and then you try to adjust your current density. Why different voltages applied in EMS for some fabricated electrode and how to interpret it? As I mentioned, I'm not an expert, but I can answer this question. So at different different potential, what happens? The kinetic changes. So at different potential, accessibility of ions in the electrode surface changes. So if your vertical line is going parallel to your y-axis, that means accessibility of your ion is increasing. And basically different, this is a typical study, at different potential we study, so that whether if we are getting close to ideal vertical supercapacitor, vertical behavior, then basically the resistance inside your system at electrode and electrolyte surface is very low. So I mean, there is a straightforward answer to this question, but I suggest you talk to expert person who is in this EIS technique. Choosing working electrode substrate code. Any suggestions on choosing working electrode substrate and coating method? Well, it depends on which kind of materials you are working with. At the same time, electrode which you are choosing. So if you are doing in 3 electrode configuration, I think it should be fine to use phase lock cell. Then your working electrode can be basically you simply make any slurry electrode or any freestanding electrode, and you deposit on your glassy carbon electrode. At the same time, if you choose like this nickel form or something, I have seen many problems with nickel redox while it is very well established. So either people are not using it wisely, but I think any kind of electrode or any system you choose, there is no basically hard and fast rules. It depends on which kind of materials and electrolyte system you are working with. So it's a very generic question. It is very difficult to answer without any details. I think I'm already very late. So I will just take a couple of more questions.
Yeah, because I just there are many questions, so I think this.
So maybe one possibility is to send me all those questions. I will try to answer if I know them. Otherwise, it will keep on going. I know when I was a PhD student, I had all these questions in my mind.
Yeah,
I used to ask to different people. So I'm happy that you have so many questions. So that means you are actually working.
yeah,
But it's very difficult. It's already 4:30, so you can
Yeah, I
send me.
think
yes, yes. Uh,
so I have to see the time.
yeah.
Yeah.
So thank you so much, Dr. Saraf, for patiently addressing all the questions from the participants. Your detailed and clear explanation made the session even more insightful. And thank you to all participants for the making this session interactive. So to end the event, I request to Dr. Pooja, please give your final remarks to us. Yeah,
Yeah,
Dr.
thank you,
Pooja, over to
Shweta.
you.
Yeah, thank you so much. And thank you, Mohit, for I think, very informative lecture and bringing it down to the student level. It's not just a research talk. It was really what we wanted.
So that's
Which
why I asked you. I mean, who will attend this lecture? Whether it is a faculty
Yeah.
or the students? Yeah.
Yeah. So because the previous lecture we covered a lecture on impedance spectroscopy and then all electrochemical techniques, and this dedicated session supercapacitor. So, and from the question we can see it served the purpose. You delivered it very nicely, and I think lots of questions are coming. If you don't mind, we can pass on still some question to you to your email. You can reply to
Absolutely.
them
Absolutely.
directly.
I will be happy to answer those if I can.
Yeah,
If I
yeah, yeah.
can.
Thank you so much. And Mohit is very expert in the supercapacitor area. And I think if the participants would like to, work with, he's also looking for some positions, students, because he's building his group. So students can also try to approach him if you find them suitable. So I would like to thank you again for accepting our invitation and delivering very nice lecture on weekend. so, from the Electrochemical Society of India, IEEE NTC and SRM, thank you very much.
Thank you
Thank,
very much
thank you,
again.
Dr. Pooja, for your kind remarks. So we look forward to seeing you all in upcoming sessions in the webinar series and also participation in NSEST 2025 conference scheduled at SRM Chennai. Yeah.
Oh, okay. I didn't know that.
Yeah, yeah. So that's also one
Have a
more
good-
thing I forgot to mention. There is a upcoming conference on electrochemistry, which is being organized by SRM and Electrochemical Society of India in August last week. So we will share the brochure and the link. So all are requested. If I think the slot is probably still available. If you are interested, please register for it and meet all the experts of electrochemistry in the conference.
Thank you very much again for inviting, and I was very happy to see the enthusiasm of all the students, and I'll be happy to have any of them in my group. So feel free to share, feel free to spread the word if anybody of you or your colleagues want to join me. Thank you.
Okay.
Thank you,
Have a
Shweta.
great day. Yeah.
Thank you, everyone. Yeah.